Okay, boys and girls, we're now looking at our second example for connected bodies. Now, previously we saw a trailer-like question. I now have a lift problem. Now, if you think about yourself standing in a lift goes up because there's cables connected to it, which effectively make it go up. But when you're in the lift, it's not the cables that make you go up or down, it's the lift itself. If you're in a lift and you're going up, it's because the floor beneath you is pushing you upwards. And that force to make you go upwards must overcome your weight. So over here, I've got an example of a little girl sat in a lift. Now the little girl is 70 kilograms and the lift is 630 kilograms. And the lift is accelerating upwards at 3.92 meters per second squared. So our acceleration here is 3.92. Now, for any question, when we're dealing with a connected body or any sort of force question, we always have to draw the forces acting on the diagram. Now, because this is a connected bodies question, we might be looking at a whole system, we might be looking at different systems individually. So I'm going to use different colors to show the forces acting on each system. So first of all, let's talk about the lift. The lift itself goes up because there is a force in the cable at the top lifting it up. And there's also weight coming down of 630 G. So we've got our weight coming down from the lift. There is one other force acting on the lift, and I'll get onto that in a second. Now, the girl in the lift has her own weight acting downwards of 70 G. Yeah, the girl is going downwards, or has a weight going downwards of 70 G. But we said that the lift is making the girl go up, so there's a reaction force coming up onto the girl, R, which is making the girl come up. Now, the thing is, when we come to talk about this force pushing upwards, due to Newton's third law, there is an equal and opposite force acting downwards onto the lift. This is the girl pushing back down onto the lift itself. So there's a force coming downwards as well, an equal and opposite reaction force from the lift or from the girl acting on the lift itself. Now, most people get confused by this. They think that it's the weight that is actually acting onto the lift, but that's not the case. Weight only acts on an individual. So I have weight, my weight acts on me and on me alone. If I'm acting on top of something else, they don't feel my weight, they feel this reaction force, which is linked to my weight, acting on it instead. So we look at the forces in this system. We have our tension in the cable, the weight of the lift over here, the weight of the girl, and we have these two reaction forces. One of the forces is the lift pushing onto the person, and there's an equal and opposite reaction force of the person pushing back onto the lift. Now, if this was a stationary lift, that value of R, or those values of R, would equal to the weight of the girl. They'd be equal to 70 G. So the lift would feel just the weight of the girl. But because there's an imbalance, because this is accelerating, that R value will change. If we think about this, the R here must be greater than the weight because that's making the girl move upwards. Now, if we look at this scenario, this is, as we said, a connected bodies question. In our previous connected bodies question, we had the trailer with the two tensions cancelling out. In this case, we can see there are two other forces that will cancel out, which are going to be those two reaction forces. Now, because it's a connected bodies question, we said we can either treat this as a whole system, or we can treat this as two individual systems, the girl and the lift. Now, for this, there is two unknowns, T and R. We could actually do this in any order, but I generally prefer to find the value of T first. I generally prefer looking at the whole system first. So I'm going to remove the F equals ma of the girl in the lift to start with. And I'm going to look at F equals ma on the whole system. And this is going upwards as a whole system. So we look at the whole system, we get T plus R minus R minus 630G minus 70G is equal to the collective mass, which is 700 times by A. Now we know A is also 3.92, and that's going to give us T minus 700G is equal to 700 times by 3.92. If we now rearrange that, we get T is equal to the 700 times the 3.92 plus the 700G, which is equal to 9604 newtons. And now we now have our value of tension. So that's sorted. That's part A done. Now part B says the reaction force of the lift on the girl, which refers to R. Now for this, we could do F equals ma on either the girl or the lift. It doesn't actually matter which one we choose. For this example, I'm going to do it on the girl because there's less forces on the girl. If we look, there's only the R and the 70G on the girl, whereas on the lift, there would have been the tension, the 630G, and the R as well. So we look at F equals ma on the girl going up. Our positive force here is R. Our negative force here is the 70G is equal to 70 times by A, and that gives us R is equal to 70G plus 70 times by 3.92, which gives us a value of 960.4 newtons. So once again, we've done F equals ma on the whole system and then on a separate system, but the key thing in this question was the diagram and understanding that there's a reaction force pushing up onto the girl from the lift and an equal and opposite reaction force pushing back down on the girl. This is always the case in lift problems and always the case in connected body questions. If you have any questions, feel free to ask. We're more than happy to help.